Our story begins in the mysterious and unfathomable realms of deep space, long before stars or galaxies dotted the cosmic landscape. Space was a swirling, tumultuous sea of gas and dust, a primordial soup from which all things would arise. Amid this chaos, fundamental forces waged a silent battle. Gravity, the architect of the cosmos, began to impose its will, drawing together particles slowly but inexorably into ever-dense clusters. Millennia passed, and these pockets of matter coalesced, growing ever denser and hotter, until nuclear fusion ignited, birthing the first stars. These nascent stars were unlike any in our current universe. They were massive, short-lived, exploding violently as supernovae that scattered heavy elements into the cosmic sea. With each explosion, the interstellar medium became richer in the building blocks necessary for more complex structures. Slowly, over billions of years, the grand dance of gravity continued, shepherding clouds of gas and star remnants into swirling stellar nurseries that gave rise to new generations of stars. These stars began to gravitationally interact, their orbits intertwining in the vast cosmic ballet, creating the spiral, elliptical, and irregular forms we now recognize as galaxies. Among countless billions of galaxies, one, in particular, the Milky Way, quietly formed. It became a crucible for the emergence of planetary systems and eventually life. Earth formed within this cosmic family, a small rocky body enriched by the heavy elements from dead stars. From the chaos of the early universe, the stars and galaxies were born, bringing order to what was once only disorder. The cycle of creation and destruction continued, driving the evolution of the cosmos. Today, as we look up into the night sky, we are not just gazing at distant lights, but at the remarkable history of our universe, a testament to the incredible journey from chaos to order. In the infancy of the universe, a condition of extreme density and temperature pervaded, marking the commencement of what is known as the Big Bang. This cataclysmic explosion initiated the rapid expansion that would eventually evolve into the cosmos we are familiar with today. However, an infinitesimally small fraction of a second following the Big Bang, something extraordinary occurred, a period of exponential expansion known as cosmic inflation. This groundbreaking concept, formulated in the early 1980s by physicist Alan Guth, proposes that the universe expanded faster than the speed of light for a brief, yet pivotal moment. During cosmic inflation, the universe ballooned from subatomic scales to macroscopic dimensions in a fraction of a second. This rapid growth smoothed out irregularities and homogenized the universe, explaining why distant regions of the cosmos exhibit similar properties today. Following inflation, the expansion rate settled down, allowing particles to cool and coalesce into the primary elements: hydrogen, helium, and small amounts of lithium. These elements would later serve as the building blocks for stars, galaxies, and eventually life itself. The concept of cosmic inflation also accounts for the observed uniformity of the cosmic microwave background, CMB, radiation, the remnant heat from the Big Bang. Tiny quantum fluctuations stretched during inflation became the seed for large-scale structures, leading to the formation of galaxies and other cosmic entities. The notion of inflation has faced scrutiny and required refining over the years, but it remains a cornerstone of modern cosmology. Observational evidence, particularly from missions like the Planck satellite, has provided compelling support for this theory, showcasing the intricate, interconnected history of our universe's earliest moments. By illuminating the dramatic genesis of the cosmos from the seemingly inconceivable to the magnificently tangible, cosmic inflation offers profound insights into the nature of reality itself. The formation of the first stars, population 3 stars. In the early universe, the first stars, known as population 3 stars, formed from primordial gas composed mainly of hydrogen and helium. These stars were massive, with some estimates suggesting they were hundreds of times the mass of the Sun. Due to their mass, population 3 stars had short lifespans, burning through their nuclear fuel quickly and ending in supernova explosions. The supernovae of population 3 stars played a crucial role in enriching the interstellar medium with heavier elements, which later generations of stars would incorporate. This process of chemical enrichment is essential for the formation of planets and life as we know it. Understanding population 3 stars helps astronomers learn about the conditions of the early universe and the subsequent evolution of galaxies. Dark matter is a type of matter that does not emit, absorb, or reflect light, making it invisible to current instruments. Despite being invisible, dark matter is thought to make up about 27% of the universe's mass and energy content. It interacts with regular matter through gravity, playing a crucial role in the formation and evolution of galaxies. In the early universe, dark matter clumped together under its own gravity, creating the first structures that would eventually become galaxies. These clumps of dark matter acted as gravitational wells, pulling in gas and dust, which then formed stars and galaxies. Without dark matter, the gravitational pull would not have been strong enough to form galaxies as we know them. Observations of the cosmic microwave background radiation provide evidence for the existence of dark matter. Computer simulations of galaxy formation that include dark matter match observations of the actual universe more closely than those that do not. Dark matter also affects the rotation curves of galaxies, causing stars at the edges of galaxies to rotate faster than expected. Gravitational lensing, where light from distant objects is bent by massive objects like galaxy clusters, also supports the presence of dark matter. The exact nature of dark matter remains one of the biggest mysteries in astrophysics. Various candidates for dark matter particles have been proposed, including WIMPs, weakly interacting massive particles, and axions. Experiments are ongoing to detect dark matter particles directly, but none have yet been successful. Understanding dark matter is crucial for a complete theory of cosmology and galaxy formation. As research continues, scientists hope to uncover the true nature of dark matter and its role in the universe. The first galaxies formed about 13.5 billion years ago, not long after the Big Bang. These early galaxies were much smaller than the massive galaxies we see today. They were composed mostly of hydrogen and helium, with very few heavier elements. The formation of the first stars within these galaxies led to the creation of heavier elements. These stars were much larger and hotter than most stars we see today. Their intense radiation played a crucial role in reionizing the universe. Reionization made the universe transparent to ultraviolet light, allowing us to see these early galaxies. Astronomers study these galaxies to understand the conditions of the early universe. They use powerful telescopes like the Hubble Space Telescope to observe distant galaxies. These observations help us learn about galaxy formation and evolution. The James Webb Space Telescope will provide even more detailed observations. It will allow us to see further back in time to when the first galaxies were forming. Understanding the first galaxies helps us understand the overall history of the universe. It also sheds light on the processes that led to the formation of stars and planets. Studying these ancient galaxies is like looking back in time to the universe's infancy. The knowledge gained from these studies is crucial for our understanding of cosmology. The evolution of galaxies over time. Galaxies are vast collections of stars, gas, dust, and dark matter, bound together by gravity. They come in various shapes and sizes, including spiral, elliptical, and irregular forms. The study of galaxy evolution seeks to understand how these structures form and change over billions of years. Early in the universe, galaxies were smaller and more irregular. Over time, they grew through processes such as mergers and accretion of gas. Spiral galaxies, like our Milky Way, have distinct arms and a central bulge. Elliptical galaxies are more rounded and lack the defined structure of spirals. Irregular galaxies do not fit into either category and often result from galactic collisions. The role of dark matter in galaxy formation is a crucial area of research. Dark matter provides the gravitational framework for galaxies to form and grow. Observations from telescopes, both ground-based and in space, have been vital in studying galaxies. Technological advancements have allowed us to look deeper into the universe's past. Computer simulations also play a key role in modeling galaxy formation and evolution. Understanding galaxy evolution helps us learn about the universe's history and future. The field continues to evolve with new discoveries and theories.